All right, well, I'll go ahead and get started here. It's just a couple minutes after 1. There may still be some people who come in. Um, Hello, everyone. Um, is that my wave button? Nope, that's my stick my arm out button. I used to have a wave button. I don't remember which one it is. Hello, everybody. I am Rob Knop. Actually, most of you have met me before. Hello, everybody. It's me. Those of you who haven't met me, I am a associate professor of physics at Westminster College, which is a very small liberal arts college in Western Pennsylvania. I've been around. I've been various different places, but that's where I am now, and that's where I've been for the last 3 years, and hopefully that's where I'll be for a long time. But we always see how these things go. And I'm trying to remember when I gave my first talk in Second Life, but it could easily have been 10 years ago at this point. We are getting very close to 10 years if we haven't passed it already. Because I know I started doing either 2006 or 2007. So yeah, it's probably been 10 years. Pretty wild. Anyway, I was originally going to talk about something different, something cool that came up. And then a week and a half or 2 weeks ago, we heard the announcement of the Nobel Prize in Physics for 2017. And so I figured I should talk about that so everyone can hear about the Nobel Prize in Physics. Is pretty exciting. I actually talked about it a year and a half ago, right after the discovery was made. And those of you who were at both talks may recognize some of the slides because I am reusing some of them. But yes, so this year's Nobel Prize in Physics was given for the direct detection of gravitational waves. And I just realized I don't have my controls on, so here we go. Where they are. Good. And it was given to these three folks. Somebody help Bruce with the voice. It was given to these three folks: Rainer Weiss, Barry Barish, Kip Thorne. I actually went to grad school at Caltech, and so I knew-ish Barry Barish. I didn't know him very well. Kip Thorne I knew a little bit better. I had a class with him, and then my last couple of years, maybe just my last year, I was a TA for Physics 1. Now, Caltech being the odd place that it is, sometimes what the professors do is TA Physics 1. So David Goldstein was the teacher of Physics 1, and then there were several people who taught the sections, including me and including Kip Thorne. So Kip Thorne and 9 other people would sit around and make tests together. So anyway, he was somebody I knew once. And they're all pretty old now. And I was talking to someone else. People were surprised because usually the Nobel Prize, they wait a little while to make sure that the discovery stands up and don't give the Nobel Prize right away. It's often given years later. And this is only a year and a half, less than 2 years later. Some people were speculating that maybe it's because some of these guys are pretty old. You don't want to wait too long. Sadly, I think Sandy Faber has died, so she will never get a Nobel Prize for dark matter, which I think is unfortunate. Yeah, even Einstein had to wait 15 years, and he was Einstein, for goodness sake. So these are the guys who got the Nobel Prize. You can see they're very excited because they all turned yellow and blue as a result of getting the Nobel Prize. I think that being at MIT and Caltech, they're a little worried that they might look a little like those are University of California colors, but who knows? Whatever. It's all good. And they all had the same citation for why they got the Nobel Prize: for decisive contributions to the LIGO detector and the observation of gravitational waves. So what I'm going to do today is tell you what are gravitational waves, why do we expect them to happen, and what is LIGO and how did it detect those gravitational waves, and what was the thing that made the gravitational waves that LIGO detected. LIGO is one of these collaborations that takes a very large number of people to accomplish. So even though the Nobel Prize was only given to the three leaders of the collaboration as a whole has between 1,100 and 1,200 people in it. Yeah, Caltech colors are orange and black, which is kind of odd. It's Halloween colors, I think, really, because everyone's scared there. So this is just a subset of the LIGO collaboration. I got this off of the LIGO page somewhere from a meeting. And, if you look at this, it looks like, I don't know, at a guess, 80 or 100 people. Maybe that's a bit of an overestimate. So it's maybe less than a tenth of the whole collaboration for LIGO. LIGO's been going on for quite some time as well. I believe it started sometime in the 80s. All I really know for sure is when I started at Caltech in 1990, it was already going. They were already working on building LIGO. And at the time, a lot of us, so in 1990, I was 22 years old, 21 years old, I turned 22. And the notion, in 1990, I was 22. I don't know if that makes me old or young. But then I was young, I know that, but I don't know if I'm old or young now. I think I'm old now, but some people think I'm young now. And we looked at LIGO, and the LIGO that they were really working on right then, they did not expect to see anything because the expected sources were too weak until they would have some upgrades to LIGO. And so they didn't anticipate seeing anything right away, although, of course, if they turned it on and saw something, that would have been remarkable. But really, they were working towards building the technology to what turns out to be now. And so at the time, to my mind, as a 22-year-old, and in retrospect, it was more than another 22 years before they would actually detect something, LIGO would never detect anything, right? Because infinity was 22 years to me, at least in terms of events that happened in my life, not events in the universe. I had a bigger perspective on that. So I never expected that I would be alive when we detected gravitational waves. Likewise, I never expected that I would be alive when we found planets outside the solar system. So the world has changed. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. Now, one point of terminology here, you will sometimes hear a gravitational wave called a gravity wave. And I know why people do that. It's because it sounds like it's the same thing. But gravity wave is actually the name we give to waves driven by gravity, and the ones we're most familiar with are waves on the surface of water. So that's what a gravity wave is. A gravitational wave is a wave of gravity. So this thing that you're looking at here, it's a gravity wave, but you might call it a surface of water wave. Gravitational wave is a wave of gravity. So gravity wave, even though sometimes it's miscalled that, it's not really the same thing. I wonder, discovering life other than us, that's going to be a close one for you and I think. Anyway, gravitational waves were predicted very shortly after Einstein published general relativity. He wrote a paper in 1916 here. Here's the thing. I look at this paper, I can't make any sense of it until this part. And when it gets to that line, I say, oh, yeah, I know what that means. But all the rest of it, I don't understand. This was his first paper predicting gravitational waves. He wrote another one in 1918, and various other people wrote things about it. It would be 100 years before they were actually directly detected. But they were a part of the theory that's been there all along. And of course, general relativity as a theory has been extremely well tested in a lot of ways by now. Huge numbers of different ways, including the GPS system has to use general relativistic corrections to get its data right. So a substantial fraction of the population of the Earth is testing general relativity at all times. It's a theory we believe. It's a very good theory. If there were no gravitational waves, we would have been extremely surprised. Do gravitational waves ever break on anything? So that's an interesting question. I don't know. All right, so the reason waves break on a beach, actually they break as they're coming close to the beach, is because there's a dispersion relation between frequency and wavelength that changes with depth. And as you get towards the beach, the water gets very shallow and the waves become unstable. And that's why they break. So there's not going to be anything equivalent to that for gravitational waves. You can get some kind of strange things for light waves. Cherenkov radiation, if you've heard of it, is when light goes into a medium. No, actually, I'm getting that backwards. Sorry, Cherenkov radiation is when a thing goes into a medium where it's going faster than the local speed of light. So light, when it goes into a medium, does slow down because of the interaction with the medium. As far as I know, there's no index of refraction for gravitational waves ever. But I could be wrong about that. On the other hand, interference definitely would happen. Interference of gravitational waves would happen if you had two sources of gravitational waves somehow emitting at the same frequency. If I could put up two big gravitational speakers. Actually, it turns out if you have regular speakers, because there's things oscillating there, they are emitting gravitational waves. It's just they're so tiny that it's inconceivable that somebody would ever detect them. And of course, you know, you're thinking, oh, he's Vizzini now, talking about inconceivable. But that's something else. Anyway, gravitational waves predicted a long time ago. Gravitational waves go through dark matter. They'll just kind of go along. Anyway, general relativity as a theory of gravity, it describes gravity as the curvature of space-time. And so I want to talk a little bit about what it means to say the curvature of space-time. Curvature is a tricky thing because saying something is curved sounds very obvious. Like, hey, look at the Earth. It's a sphere. It's curved. Well, okay. But the curvature of the Earth is what we call an extrinsic curvature. So here's vocabulary word number one. It's a curvature that you see because we're in 3 dimensions and the surface of the Earth is a 2-dimensional surface that is curved within those 3 dimensions. And that's great, but the curvature of space-time we're talking about is an intrinsic curvature. So you probably could have guessed that was the opposite of extrinsic. It's a curvature in 3 dimensions, and we don't go outside of it to see it. In fact, we don't see it directly. It just is space. So what does it mean to be curved in that case? What it means is that the postulates, Euclid's postulates, don't necessarily work, and the geometry becomes non-Euclidean. So the way to kind of think about that is think about it in 2 dimensions, because we can then be hyperdimensional 3-dimensional creatures and take 2-dimensional spaces and embed them in our 3 dimensions to get a sense about curvature. So imagine here that this is flatland. There's only 2 dimensions. Left, right, forward, backwards. Up, down doesn't even mean anything. You know, it's like if I wanted to put in the X direction and the Y direction and the Z direction, I can do all those things, but I can't find a direction that is perpendicular to all 3 of those. Just as a 3-dimensional person, I can't do that. But here, this is a flat space. This here is also a 2-dimensional space. So again, creatures can only move along the space, and to them that would be moving, you know, if they would move in a straight line, as straight a line as they could. But that space is curved. Now we outside it can see, oh yeah, it's bent. It's clearly curved. How would creatures inside the space measure it? Well, one thing they could do, if you're over here in this flat space, and you measure the angle at all 3 corners of a triangle, where you go on a straight line from one to the next, you get 180 degrees. If you do it here, because the thing is bowed out, right, this one looks about right, but this one's a little bit, the angle's a little bigger. Here, the angle's a little bigger. You'll get something bigger than 180 degrees if you try to measure the 3 interior angles of the triangle here, even though you went in as straight of a line as you can, and you did not detect yourself doing anything other than going in a straight line, going from here. And even here, it's like, no, that's a curved line. Well, no, it's going straight through the space there, through the surface. So that's a way you can measure intrinsic curvature. Another way is, because intrinsic curvature leads to gravity, is that if you take a couple of things and you let them fall freely, and what that means is you have nothing other than gravity acting on them. If they start to diverge or come together, that tells you that they're not in a flat space. Now, actually really doing that can be kind of tough, but we've effectively done it. We've had satellites designed to measure things like frame dragging, which only happens in general relativity. And yeah, Vic has just pointed out Flatland. It's a fun novel to read. It's thin, it's short, it's mostly a parody of Victorian society, but it also gets you thinking about what it's like to think in higher dimensions. And so for that reason, I've sometimes assigned it when I've taught general relativity. Alexander also points out that, yes, curvature in general relativity is actually, we live in 4 dimensions, 3 space and 1 time, and then there's an intrinsic curvature in those 4 dimensions. So it's not just space that's curved, it's time that's curved as well, and that becomes kind of a weird thing to think about. So, okay, so that's what this is. Now, you will sometimes see diagrams like this. They're called embedding diagrams. What you do is you take this. So this left panel here is just a picture of space. Here's a star. It's a white dwarf star. You can tell that because it's white and it's small. It doesn't have a beard. You think, because, like Gimli, you'd think they all have beards, but whatever. It's white and it's small, and then here's a grid that I have just put in the XY plane, right? So there's X, Y, and Z, 3 axes. I've put a grid in the XY plane. Well, because of the mass of the white dwarf, this XY plane is curved. Now, it doesn't curve up or down into Z. It just is intrinsically curved. In what way? Well, it has the same geometry as this. Now you're going to say, but Rob, you just said it doesn't curve down into Z. And look, there it's curving down into Z. Well, it's not. Here I have only plotted X and Y. I have not plotted Z on this diagram because I wanted to use the third dimension for something else. The third dimension is sort of a abstract third dimension that we use so that this non-flat surface has the same geometry as this does in its non-Euclidean space modified by mass. So what does that mean? Well, for example, suppose you start here and you go all the way around the circle, all the way around the star at a constant distance, and you measure the circumference. That was exciting. You just did that. Now, you go through the middle, but you have to stay in the space, right? So it's like you dip down. Not really that. But you go through the middle and across, and you measure the diameter. If you take the ratio of the circumference to the diameter, you will not get pi because the diameter was longer. We can see that here, right? Because you didn't just go straight across, but you had to go through this little curved thing. You don't get pi. Well, what I'm saying is if you do the circumference here around a real star, right, and then you do the diameter, you go across, you will not get pi for that ratio. So Baragon asks, the lines are smooshed together, and the answer is kinda. What it really means is that, when you're far away, one grid spacing is, say, I don't know, let's call it 10 kilometers, 100 kilometers maybe is probably better for a white dwarf star. Maybe 1,000 kilometers for a white dwarf star. It's probably about right. So one grid spacing is 1,000 kilometers in both directions. When you get close, one grid spacing is still 1,000 kilometers tangent to the star, but radial to the star, one grid spacing is more than 1,000 kilometers. So sort of they get smushed together, but the problem is that you can't really draw it in two dimensions without getting something wrong. For exactly the same reason, you can't take the surface of the Earth and draw a two-dimensional map of it without getting something wrong, because it just doesn't map perfectly to a flat space. So when you see these diagrams, it's not that anything is really going down here. There's no, people sometimes use the analogy, oh, it's like a bowling ball on a rubber sheet. And I don't think that's a great analogy, because there it's the gravity of the bowling ball pulls down. Yeah, it helps you understand what to think about, what surface to think about, but it misleads what the surface is really showing you. So what this really just says is, this non-Euclidean surface that I've drawn as if it were Euclidean has the same geometry as this curved surface in a three-dimensional Euclidean space. And so that gives us a sense, kind of what curved space means. I know the very first time I heard about this was my freshman year of college. We had a special relativity section in our physics class, and Professor Helliwell came one day to tell us a little about, Professor Helliwell was a relativist, to tell us about general relativity. And he said that, space is curved, gravity curves space. And I didn't even understand what he was trying to say. So at the end, I went up to him and says, how do you curve space? His answer, put some mass there. And this was a classic case of me asking a question, him giving a correct answer, but not to the question I was trying to ask. And what I was trying to ask was, what does it mean to say space is curved? Because if you take a piece of paper and you bend it, you've curved it up into the third dimension. Where do you bend it to curve? And the answer is you don't bend it anywhere. It just becomes non-Euclidean. And if we've studied geometry, that's tough for us to digest. But that's kind of how it works. Well, all right. Oh my goodness, I have differential equations. Who wants to see differential equations, and who wants me to skip the differential equations? Let's vote. Oh, so which? Tell me, you want to see them, or you want me to skip them? Matrix algebra, yeah. Matrix algebra would be a good name. All right, at least two people want them, so I'll do them very quickly. I apologize to those of you who do not understand differential equations. We have this thing called the metric. It's a little, basically a 4x4 matrix. Oh, really, it's a tensor, but you can represent it as a matrix that tells us how space works. In special relativity, you may have heard that space becomes space-time. How does that work? Well, this here, x, y, and z, is just your regular, everyday, normal space, three-dimensional space. T is time. This thing is called the space-time interval. So even if you don't understand the equation, just by looking at the fact that we've got space and time mixed together, you can see, hey, they have an equation that mixes space and time together all into one thing. Now, it's weird. It's like, why are you subtracting space? Well, it turns out it's a convention, but you have to subtract either space or time in this equation to make it all work right. And what do I mean by work rate? What I mean by work right, I mean um, give the right predictions that we have verified with experiment for special relativity. So that's great. So, and if you look at this, x squared plus y, in fact, ignore the t and the z for now and pretend that this ds is like a length. Yeah, what Mike says, it's exactly like Pythagoras. X squared plus y squared is length squared. Again, with little negative signs to make things interesting. So x plus y plus z squared, you square all those in Adam. It's three-dimensional Pythagoras. Then you have t, and it becomes space-time. That's great. So this is what flat, normal, everyday space would look like. When you go to general relativity, you have different things besides just 1 and -1 in here. And here's where the differential equations start to get really nasty. We can approximate very small disturbances to flat space. So assume you're in a space and there's nothing nearby, and a small disturbance is going through it, i.e. a wave. And one way to figure out that wave is we approximate this little thing that tells us the curvature of space-time with the undisturbed one and a small disturbance. And the idea is that h is very little. H is very small. And so this one is the undisturbed one, the disturbance, and I've chosen a disturbance that only happens in these two places. It only depends on z and t. So what that means is the wave is moving in the z direction, and it depends on t. So when I figure out this interval now, dt and dz look the same, but I have something added on to dx and dy, right? That's what we've done. And I've mentioned that I have cheated a little bit. I shouldn't have had 0 here and here. What that will do is lose me one of my two polarizations. Okay, so then, and I'm now going to skip all the hard stuff. In reality, what I did is I stuck it into Maxima, and I told Maxima to tell me the answer, and then I looked at what Maxima gave me, and I knitted all the terms to more than first order in h, because h is very small. And it gives me these actually pretty simple differential equations. I mean, you may look at them and wonder what you're looking at, but if you do physics, you may recognize this as the wave equation. This basically says something changing in time and something changing in space combined together to subtract out. And that's a wave. So this is going to give us sinusoidal waves for both this hy and this hx. The rest of these things tell us that for what we've got here, hy has to be negative hx. All right? So the result of all these differential equations, and I'll get past them so you don't have to worry anymore, is that we have waves. The equations of general relativity, if we allow for a small disturbance, give us basic waves that move at the speed of light in the curvature of spacetime. So it's distances between things. The distances in spacetime itself is what is waving. If you tried to derive a wave equation for the surface of water, you would get the height of the water as a function of, say, along a line, say x and t is what you would see that varied in the differential equation. So here it is space-time itself. So I actually have a three-dimensional object that Padioplasma made that I will res out here. It may take a moment. Where is it? Yeah, here it is. It may take a moment to res in for you because it uses Sculptes. And what I'm going to do is what I really should not have done was push my middle mouse button, which turned off my my microphone. So how far was I when you stopped hearing me? Hear me talking about the circle and the ellipse on the end here. Sculpties. Oh my goodness. All right, fine. So I pushed the middle mouse button, and I accidentally clocked Chantal on the way by, and I apologize for that, and you didn't hear any of that. So what I want you to do is zoom in on the end of this here. Well, you'll see the little compass that goes from 0 to 330, really up to 360 degrees. And if you just look at the end of that, you can see this oscillating ellipse. It goes from a vertical stretched ellipse to a circle to a horizontal stretched ellipse to a circle, et cetera, over and over again. That's what happens with these gravitational waves. And that's, remember that hx had to equal minus hy? When it is stretched horizontally, hx is positive, but it's squished vertically, so hy is negative. That's where the equations come into this. This is how a gravitational wave works. Basically, if you imagine little tiny pieces of dust floating around in space, this is how they would be moved around as a result of the gravitational wave coming through. You can think of it as being pushed by gravity, because that's sort of what it is, but we don't call gravity a force in general relativity. It's just the curvature of space-time, and this is what space-time does. And if you zoom out and you look at the 3D, you can kind of get a sense of what a propagating wave, gravitational wave, does to space-time as it goes by. So what I was mentioning, I don't know if I was on when I mentioned this. This was actually created by Plasma, which is why it's over at the Exploratorium. And she gave it to me when I gave a talk about a year and a half ago. So, not wrong waves. I don't understand. Anyway, so this is a gravitational wave. Yeah, I don't know what you mean by gravity wave. Gravity waves are not longitudinal. Gravitational waves are actually transverse, and they have this quadrupole form to it where it stretches one dimension while squishing the other. So I tried to indicate this on this slide as well. You have a wave going along this green arrow. So this is a snapshot in time. This grid here just represents places in space. So right here is right at the middle point of the wave, where on that thing I've raised out, it would be a circle. Well, so behind it, everything is squished in one direction. So it's squished left, right, and stretched up, down. Then in front, it's squished up, down, and stretched left, right. And then that would propagate through space, like what you see on the little sculpty thing that I've raised out here. Yeah, that's right. And then the real thing is, if you can look at it at a diagonal angle, you can see that they're out of phase. So when the parts that are up are stretched up, down, are squished left, right. That's kind of the key thing. All right, so that's what a gravitational wave does to space. Well, really, to get them, all you have to do is take something big and wave it around, and gravitational waves will happen. If you want to detect them, you need to take the biggest things we can and wave them around as fast as you can. And so it helps to have a really, really dense object like a neutron star or a black hole, because then they're big and they get really close together and you can get strong waves. So this image is supposed to represent two neutron stars coming together, and as they orbit each other, they the argument, okay, I'll have to. And then so Vic, when you say gravity waves, do you mean gravitational waves, or do you mean like water waves? All right, I may look at that later. But in any event, this represents two neutron stars coming together. As they orbit each other, they lose energy. They radiate it away as gravitational waves, and so the orbit spirals together. And the result is that you should see them come together. Now, neutron stars are neat because one of the things they do is they can pulse. In fact, I think I have a 3D object for this as well. Let's see if I can find that. Yes, here it is. So here's a pulsar, and basically think of this as the surface of a neutron star. Up on the slides, you see I've drawn this big magnetic field for the neutron star. Well, the magnetic field can get really strong for a neutron star. So if there's charged particles, they will get trapped in the magnetic field and funneled down, and where they hit the surface of the neutron star, the gravity of the neutron star is very strong. So they'll fall in very fast. They'll hit the surface of the neutron star, and there will be a hot spot. And so that's what you're seeing here. If the neutron star is rotating, and if the axis of rotation is misaligned from the axis of the magnetic field, when the hot spot is pointed towards you, you will see a pulse, a bright pulse. And then when it's no longer pointed towards you, you won't see a pulse anymore. And these can rotate very fast. There are pulsars that rotate hundreds of times a second. There's some that rotate every few seconds. So I've got every few seconds for the demo here, so you can kind of see what's going on. But what that means is they're very precise timers. In fact, it was only in the last couple of decades that we could make atomic clocks on Earth that were more precise timers than pulsars. So pulsars give us very precise timing, and then if you have two of them orbiting each other, you can use that timing to figure things out about the orbit, right? So when it's coming towards you, subsequent pulses are emitted closer together or closer towards you. They don't have as far to go. You can measure those kinds of things. And when the one is moving away from you, the pulses get more spread out. It'll be a longer time between when they're received. So you can use that to do very precise timing. Gravitational radiation or gravitational waves, what general relativity predicts is that as they emit gravitational waves, the orbit should decay, and we should be able to observe that with the timing. So, and here is the pulsar system that was actually observed. This pulsar system garnered the Nobel Prize back in 1993. It's a binary pulsar system. So actually, one's a pulsar, the other neutron star, I don't think is actually pulsing, or if it is, it's not pulsing as strong. They're in an elliptical orbit, and especially when they pass closest, they emit a lot of gravitational waves. And general relativity allows us to predict what's the rate at which energy should be lost due to those gravitational waves. So this is a plot. So Hulse and Taylor are the guys who discovered this. And the guys who discovered this. And this is over time, from 1975 all up until, 2007, I think. If the pulsars were just orbiting each other the way Newton's laws say they should, and there was no decay, they would stay on this horizontal line. The spots are the data. And then the horizontal, or not the horizontal line, the curved line is the fit using general relativity. So it's general relativity's prediction of what you should see. And notice the data match general relativity exactly. So this, I would say, is an indirect detection of gravitational waves. We actually knew they existed, not only because this extremely well-predicted theory told us they did, but also because we had seen an effect that happens because of gravitational radiation. So this was an indirect detection of gravitational radiation, and it matched exactly what general relativity predicted. So that was before. But now we've got a direct detection of gravitational waves that happened with LIGO. So LIGO, and I'm going to actually take away my objects here, just because I think they're distracting. Yeah, it is. It's amazing, well, how people think. You can put that in a whole bunch of different contexts, and there's lots of different ways to be amazed. This is LIGO. It's there's two of these guys. There's these long arms here. What they are is big evacuated tubes that they shoot lasers through, and they bounce off of mirrors, and they collect everything back here and analyze the data. There's actually two of them, one in Hanford, one in Louisiana, and now in Italy there's a third detector called Virgo that the most recent black hole merger detection was detected by all three of them, actually. So LIGO and Virgo work together. The way LIGO works, so I mentioned in these long arms that there are lasers bouncing back and forth. And so what these lasers are doing, so these are not gravitational waves, these are laser light waves. It starts over here. It hits this mirror, which is a partially silver mirror, so some goes through and some reflects. The stuff that goes through goes and downs and bounces off a mirror 4 kilometers away on the far side, right? So then it bounces off, it's reflected back here, and then some of it goes through the partially silvered mirror. Also, of this wave, some of it bounces off immediately. Now, if the distance between the mirrors is just right, so that an integral number of wavelengths fits between the two mirrors. So here I've just got 2 wavelengths. Of course, in reality, it's a whole lot more, but it's easier to see in the picture with 2. If an integer number of wavelengths fits between the 2 mirrors, then the 2 waves will be out of phase from each other. And what that means is they'll just sum. They're both high at the same time. They're both low at the same time. They will sum together and give you a brighter reflected beam than you would get if you just had one of the 2. On the other hand, suppose the mirrors were closer together. So I'll put my laser where the mirror is, and I'll go to the next slide, and you can see, oh, yep, they're closer together. Now, it's actually a half interval wavelength. So this is that's 1 wavelength, and here's actually it's not half interval, it's integral, whatever. It's off by a quarter. There's reflection issues we have to think about. It's off by a different amount, and as a result, the two waves that are reflected are now out of phase. This one is high when this one is low. This one is low when, or sorry, this one is low when that one is high. The two will actually cancel each other out, and that's called destructive interference. And anywhere between here and here, you will get a different amount of interference. And so by measuring how bright, as a function of time, this reflected beam is, you're measuring differences in how far apart these two mirrors are. So is this like the Michelson-Morley experiment? Kinda, I guess. It's very similar to the Michelson-Morley experiment in that it uses interferometry of two light waves, except for Michelson-Morley, they interfered light waves that are originally at 90 degrees to each other. Here we interfere light waves that are just straight along. We do have 90 degrees, but it's for a different reason. But it's using the same light physics that Michelson-Morley used. Yep, and so changes in position of the mirror is due to the gravitational wave. So what they're trying to find is look for wiggles in the mirror due to gravitational waves. Now, if you think about it just a little bit, you can think of a whole bunch of other reasons why mirrors might wiggle, like earthquakes or trucks driving by can cause mirrors to shake and mirrors to wiggle. So they need to isolate these mirrors as much as possible from all other sources of vibration. And what's more, they have to understand the noise sources well enough that they can subtract them out. So this is an incredibly difficult technical challenge because the gravitational wave signal is so small, as we'll see in a moment. So, they can measure shifts of a fraction of a wavelength, which is already pretty hard, but also they have to isolate the mirrors and they have to be able to subtract out their background so that they'll really see anything. So, all right. So remember, we said that gravitational waves are ripples in space-time. So imagine that the arm of LIGO is along this direction. So you see the mirrors closer together, and then the normal distance, and then farther apart as a gravitational wave goes by. How much does it change? Right? And remember, this is 4 kilometers is how long one of these is. And the answer is it doesn't change very much. The thing they use to measure how much it changed, the name is just strain. And the basic idea is that this dotted line shows what's the resting length of a thing. It can be anything. Strain is actually used in engineering also to talk about what happens when you put stresses on a beam and how much does it stretch out and things like this. And you may have heard of Young's modulus and things like that. But strain itself is just how much is it stretched. So you start with the rest length, then it changes to some length L plus delta L. So delta L is just how much the length changed. And we define strain to be the change divided by the original length. So delta L typically is going to be small. So epsilon is typically going to be a number because this is a length and that's a length. It's unitless. Tends to be a lot less than 1. All right, so remember, the length was 4 kilometers, which is 4,000 meters. The typical strain we're talking about for these gravitational waves is 10 to the minus 21. I'm not going to say that with pointing all the zeros because I'll lose count of my zeros on the way in. Suffice to say that it's dinky. Multiply this number by this number, you get what the delta L is. It is 4 times 10 to the minus 18th meters, which is dinky. Now, it's very tempting anytime you see 10 to the minus something to think it's dinky. But we got to put this in context. They use infrared light with their lasers. So it's very dinky compared to the wavelength of light. Oh my goodness, that's dinky. What's more, it's dinky compared to the size of an atomic nucleus. I have to admit that I'm a little bit boggled that they can detect shifts this tiny. And that gives you a sense as to why it was so amazingly difficult to do, that they had to have really good isolation systems so that the mirrors aren't going to be wiggling around as a result of some ant walking along the surface of the ground 5 miles away, and those vibrations causing the thing to wiggle, to detect these tiny gravitational waves. So they're really, really small, and this is why it took 100 years to detect them. The signal is so amazingly weak, even when black holes run into each other, that it takes a really powerful detector to find these things. If you want to see this slide, zoom in on this slide because the writing is kind of small on it. These are sensitivities. The horizontal axis tells us the frequency of the wave. So yeah, so the L plus DL, I mean, the L plus DL can happen for sort of any reason, but the ones we're looking for is because of the gravitational waves coming through. Yeah, this is actually a really cool slide. You can find, if you Google this, there's a whole bunch of buttons you can click to turn on and off various things for different sources and different detectors. It's kind of fun to play around with. This sensitivity, horizontal is frequency. This is 1 hertz here. This is 100 hertz. So the signal here, this here is the first gravitational wave that was detected from merging black holes. Its signal was around 100 hertz. What's interesting about that is 100 to a few hundred hertz is also the frequency of sound that your ear can hear. But this isn't sound, it's gravitational waves. All right, so this is the frequencies of the waves that we would expect. Here is the strain. So let's see, 10 to the 18. 10 to the minus 20, I'm sorry, 10 to the minus 21 is here. Right between 10 to the minus 20 and 10 to the minus 22. So that was the thing I showed you before. So if you go over 10 to the minus 21, going as horizontally as I can, that right there you go is the signal that I gave you as an example, and it's right in the middle of this reddish signal here. Now, these curves here are curves of sensitivity. So LIGO, as they have it right now, is this curve, and Virgo is this curve. They both dip down to about here. You'll notice they're only sensitive from frequencies of, I don't know, 80 or something, up to frequencies of 200, maybe 800 hertz, something like that. So slower waves, lower frequencies, or faster waves, they won't be able to detect. And, but fortunately, this signal was right, the signal was strong near the dip of what they saw. Down here is advanced LIGO. Over here, LISA is a spacecraft, actually. It stands for Laser Interferometric Space Array, maybe? I don't actually know what LISA stands for. But it's going to be a spacecraft that'll work just like LIGO, but it'll be in space. It'll be bigger because it's in space and freely falling. You won't have to worry about vibrations from trucks driving by. You probably do have to worry about vibrations from the solar wind varying, but whatever. I think if you go back in time 10 or 20 years, LISA was probably supposed to be up by now. I don't expect it to go up during my lifetime. I hope I am surprised about that. Yeah, okay. Laser Interferometer Space Antenna. Very good. And LISA, you see, is sensitive to a very lower frequency because it's so much bigger, partly. But that'll detect different things. And then the colored spots are the kinds of things we might expect to see. So right here, this big red thing, and also sort of the pinkish red thing here are compact binary mergers, or inspirals. That's when you have two really big things, either black holes or neutron stars. So that's what makes them compact, and binary because there's two of them. In spiral, they're spiraling in towards each other and merging. Those are the kinds of signals we can hope to see right now. With advanced LIGO, we might be able to directly see core collapse supernova. We might even be able to see some pulsars if they're not perfectly regular rotating. And so that would be really cool. We might start to get a lot of signals. With LISA, notice here it says massive binaries. We should be able to see the gravitational waves from black holes orbiting each other, even if they are still a long time from merging with each other. So we'll be able to see a whole bunch of other stuff. One of the things that makes me sad is the this here supermassive binaries is one of the things I want to see because it's at the cores of galaxies, supermassive black holes, and alas, LISA won't be able to see them. So, well, we can just weep. But also, LISA would be able to see type 1a supernovae. Oh, I'm sorry, no, type 1a supernovae down here. Nobody gets those. But they'll be able to get resolvable galactic binaries. We're talking binary pulsars and things like that. So, there's some pretty hope. There's some hope, that we'll actually see interesting things. But right now, we're already seeing interesting things just with LIGO. So here it is. This is the graph that got a Nobel Prize, or at least this is the graph that summarizes the signal. As I mentioned before, there are two LIGOs. So there's one in Hanford, Washington. There's one in Livingston, Louisiana. This here is just strain compared to. I don't sound like I'm sad much. I'm sad all the time. There's not enough kitties. This is strain in, compared to sort of rest strain. So does it get smaller or bigger in units of 10 to the minus 21, right? So this is very dinky. And what you see, also the time axis is worth looking at because it goes from about 0.25 to 0.45. That means we're looking at a fifth of a second. So over the course of a fifth of a second, the signal goes from, here you can sort of see the noise. The frequency was high enough that they weren't able to detect it. The noise was too high, to being detectable, to the wavelength getting shorter, which means the frequency getting higher, right? Frequency gets higher. Sorry, not the wavelength, the period, because we're talking time here. Frequency gets higher to then calming down and being all flat again. So if you think about what the sound of this would look like, it starts it starts quiet, then you can start to hear it, but it's a low pitch, and then it goes to a high pitch, and then it turns off. So it's sort of a zip. And I think the LIGO people actually did feed the signal into a D to A, or just basically into a speaker to see what it would sound like. Something like that. Hanford saw this. Louisiana saw it. They both saw the same signal. This is key because if they hadn't both seen the same signal, we wouldn't have believed that it was real, that we would have thought, okay, that's just something wrong with one detector. They're very far apart. The same truck is not going to hit both of them. If it's an earthquake that hits both of them, we'll probably see the earthquake somewhere else. It hits both of these. The time delay we can figure out because it takes time for the gravitational wave to get from one to the other. Not very much time because it's going at the speed of light, but it does take time. But also impressively, what they have here, the gray line down here is taking the data and reconstruct it using various different data processing techniques. So it takes this and you smooth the noise out, you get the gray schmear, and the width of the schmear tells you something about the uncertainty, and then the two techniques tell you something about what's the uncertainty as a result of the schmearing technique. The red line is what you would predict from general relativity, and what's really cool is that the signal fits perfectly. So this tells us a couple of things. One, it really is a gravitational wave because general relativity can reproduce it. But even more than that, this is the signal from two black holes merging, and it tells us that the gravitational waves emitted by two black holes merging is exactly what we expected. And this, I believe, is the first time we've really tested general relativity at the event horizon of a black hole. We've got a million tests of general relativity, and they're great, but almost all of them are in the weak gravitational regime, right? So the gravity around Earth is the weak gravitational regime. Mercury's orbit is slightly wrong if you use Newton's laws and can be fixed with general relativity. But again, around the sun, that's in a weak gravitational regime. This is testing gravity in the strong regime, and it still works, which means, hey, great, general relativity is still on. One of the funny things about this, of course, is that when it was discovered, there are all kinds of headlines saying Einstein proved right. Yeah, and so that's a headline that's been used for 100 years now, and we'll probably keep using it. Sooner or later, people are going to realize that we shouldn't be surprised that we have just confirmed a prediction of general relativity, that Einstein has been proved right a lot about this stuff, and that the next time it happens, it's not like there was any doubt. If we ever find a contradiction, that would be huge news. And it's big news that we confirm it, but it's not like this proved Einstein right. It's like, hey, general relativity still is working, rather than, oh my God, it turns out Einstein was right after all. Who'd have thought? He was right about that. There's some stuff he was wrong about, but that's different. I'm going to skip that slide. I'll come back to it later if you want. So as I've mentioned a few times, this is the result of two black holes merging. This image sort of puts that all together. So out here where the wave is, and this is the theoretical wave. So this is a reconstructing template, but the noise was too big to detect when it was all the way out here because the wavelength was too long. They start out here, they're in spiraling. This is where they just barely start to detect it. 0.2 seconds later, they've merged. So in the meantime, they've gone from far apart to closer to right merging. And then, of course, when they first merge, it's not exactly a sphere. So then it settles down back to a sphere, or really a stretched sphere because it's rotating. And then space-time completely calms down after that. We have to go to conditions more extreme than large to find deviations from Einstein's theory. I don't know. It just means that we haven't found a deviation here. It's conceivable that we will find a deviation in other places. Some people suggest that rotation curves of galaxies point to a deviation from Einstein's theory. That's the whole Mond thing, but that's not I don't know if it would take something either more extreme, but at least something different would have to do it. Anyway, so this is what happens when the black holes are merging, is when you get the strongest burst and highest frequency waves, and then kind of zhoop, goes down and then calms down. And so this is what LIGO saw. This is what they were doing. And the first detection of gravitational waves was these two colliding black holes. There were two black holes. We call the bigger one the primary and the other one the secondary, although they're pretty close. 36 times the mass of the sun. So think about that for a moment. It's a black hole 36 times the mass of the sun. That's pretty big. Unless you study galaxies, and then you're used to black holes that are millions or billion times the mass of the sun, and you think this is dinky. But okay, compared to the sun, it's pretty big. The other one was pretty close. Well, here, Vic, the funny thing about him being wrong about cosmological constant is that he was right first, and then he was wrong. So, yeah. I think where he was wrong was I don't think he ever really believed the stochastic nature of quantum mechanics. And that's the thing I think that he's got. I think that's the thing that maybe one day we'll discover he was right after all. But for now, that's the thing it looked like he was wrong on. Anyway, these two black holes come together and they merge. Now, here's a fun thing you can do. If you ignore the uncertainties for now. We'll come back to that in a moment. If you add 36 to 29, you get 65. And yet, the merged black hole is only 62 solar masses. What that means is that if you take E equals mc squared to turn mass into energy, 3 solar masses times c squared of energy was radiated away as gravitational waves in this merger. That's pretty impressive. And that's why it takes things like gravitational or black hole mergers for us to see gravitational waves, because it's such a small effect that it takes a really huge wave for us to see. Now, what's also interesting about this, one thing about the black hole, the final black hole, we expect is spinning around 2/3 as fast as a black hole can spin. There's a maximum spin that colloquially is basically when the event horizon is moving at the speed of light. This black hole, if you do cosmology, it's at a redshift of 0.09. What that means to a cosmologist is that it's right on the boundary between being in the local universe and being at the very distant sort of homogeneous part of the universe. So it's far enough away that it's far away. Anything closer would be not that far away, at least if you're a cosmologist. 400 megaparsecs. And what is 400 megaparsecs? Well, here's a picture of space. This is the 2-mass survey of galaxies. It's an infrared survey of galaxies. It looks like galaxies only go out to here. That's just because that's the sensitivity of the survey. More distant galaxies were too dim to be able to be seen by the galaxy. Right, here's us. If you've heard of the Virgo Cluster, the Virgo Cluster is a cluster of galaxies 65 million light years away. What that means is the light we see from the Virgo Cluster was emitted when the dinosaurs were looking up and saying, hey, is that an asteroid? And now we're seeing the light. So that's 65 million light years away. It's the closest really big cluster to ours. Right? So, yeah, there's lots of clusters of galaxies all in this region. Here is 300 megaparsecs. So to get to 400 megaparsecs, it would be about this distance. It's about 1 billion light years. So 300 million parsecs, about 1 billion light years away. That's how far away these black holes were. So that tells us a couple things. One, this doesn't happen all that often because we've only seen a handful in this volume. But it also tells us, hey, we can see them pretty far away, which is pretty cool too. This is a summary. To date, there's 4.5 detected black holes. Why do I say 4.5? One of them was actually just below the threshold of signal to noise for the LIGO to say, hey, it's a good detection. So it was probably real, but there's a big enough, few percent chance that it was actually just a random fluctuation they saw instead of an actual signal, that they don't call it a full detection. The other 4, including the most recent one, and I don't know which of these is the most recent, but the most recent one was seen by Virgo, this detector in Italy, as well as LIGO. We've seen several of these black hole mergers by now. And a great way to visualize them is this plot where the horizontal axis doesn't really mean anything, but the vertical axis is the size of the black hole. Down here, you have a bunch of black holes between about 4 and 9 times the mass of the sun, and then a bunch more that go from 10 up to, 16 times the mass of the sun. All of these guys are black holes that we knew about because they're in X-ray binary systems. X-ray binary systems happen when you have a black hole, or a neutron star, it turns out, but these ones are black holes, orbiting are mutually orbiting another regular star, if they're close enough, the black hole pulls material off of the regular star, which then builds up in an accretion disk around the black hole. That accretion disk can get extremely hot and can emit X-rays. One of the coolest ones, if you want to look it up, is SS443. That's a pretty exciting object. If you learn about it, it has jets shooting out of it. It looks like a quasar, only it's small and in our galaxy. One of the most famous ones is Cygnus X1, which it's the brightest X-ray source in the constellation Cygnus. So both of those, I don't know which spots they are, but both of these are some of these purple spots. We've known about these black holes for some time now. There are also, what's not plotted on here is the black holes that are at least 1 million times the mass of the sun. And so that's what we get at the cores of galaxies. Well, and now we've got, well, you know, it kind of was 8 and became 4 because they merged. Black holes that, it's like this one started with one about that size, but notice these here, and this original detection started bigger than we expected, in a sense, because we haven't seen any black holes that big before, at least of stellar mass, where it's only a few tens of masses times the mass of the sun. So you have these two that merged to this one, and that's what the rest of these indicate. That here were the two original ones, that's the merged one. We only saw those black holes because of the merger event. So LIGO has done a couple of really amazing things for us. One, it has detected gravitational waves, something very long predicted by general relativity that we always hoped, right? We want to see gravitational waves. If we don't, it means there's something up with general relativity. But we are also seeing what the LIGO folks have been telling us for decades, that once we have gravitational waves, it will open up a new window on the universe. We will be able to look at objects in ways we haven't looked at them before, and we will be able to see things that we weren't able to see other ways, and here we're doing that. We haven't seen black hole mergers before, and here they are, we're seeing them. And we're seeing black hole of masses that we haven't seen before. The only reason we see these is because there's stuff around it that glows in the intense gravity of the black hole. So here we're seeing the gravity, the gravitational waves of the black hole. So LIGO is telling us about black holes as well as telling us about gravitational waves and general relativity. And so that discovery, the discovery of gravitational waves, and again, it wasn't really, I mean, they were predicted 100 years ago. Couple decades ago, they were detected indirectly, but just a couple years ago is when we first detected them directly, and that direct detection is what got the Nobel Prize in Physics this year. So yeah, here's my summary. I think I already said all of this stuff, right? We've detected gravitational waves, the models work, and these black holes are out there running into each other. Let's keep looking for them. And LIGO and Virgo are going to keep finding these because they're happening. And hopefully this will help add some impetus to actually building LISA. Once upon a time, NASA was going to build it. NASA gave up on it. Now the Europeans are working on it. I hope they really do it so that we can start seeing this other stuff. So anyway, there you go. That is the 2017 Nobel Prize in Physics. So at this point, if anyone has any other questions, I'd be happy to take them. All right. Yeah. Thank you all. General relativity it's really cool, but it's, the math gets really hard really fast. All right. Well, thank you all. Oh, yes. The question. Gravity waves from space. Let's see. I am not familiar with this. I'd have to take a look at it. Oh, yeah, I'll come back to that slide. Slide that I was going to go back to was just a different way. Would we be able to detect stellar mass black holes being consumed by, here, actually, I think I can answer that. because I had a slide that had that on it. So let's go back, back. I'll come back to that slide in just a moment. But that is, oops, I went too far. That is one of these here. See where it says extreme mass ratio in spirals? So that would be a stellar mass black hole getting swallowed by a galactic centered black hole, would be an extreme mass ratio in spiral. And that's this. So that's the kind of thing we could see with LISA we would not be able to see with LIGO. Now, the slide I skipped, basically what this does. So here we plotted strain versus time. But you could also plot how strong the signal is as a function of frequency, right? The frequency is higher here and lower here. And so if you plotted the frequency versus time, the frequency would be going up. That's what this is a plot of. So same time is on the previous plots, but now we're plotting frequency. And then a brighter and yellower means a stronger frequency, right? So here's the amplitude of waves at that frequency. If they're not perfect sine waves, it'll be smeared out, although these are pretty close to sine waves. And so this sees the kind of sound you can see where it starts quiet, and as time goes by, it gets louder and also whoop, goes up to higher frequency and then dies out. Right? So there's basically nothing out here in time. Right about here is a 440A, concert A. So I don't know if I can do that. I don't have perfect pitch, so I was probably within a factor of 2 of a concert A, but that's all the best I can hope for. So this would be, all right, I'm going to talk like a violinist now. Down here at 220 would be an A on the G string. And then if you go another octave down to 110, you're down playing the cello. So this is, that's what this would sound like. It sounds like we have a cat actually that does the same thing. When she's hiding under the hassock and one of the other cats is annoying her, she gets there and she growls and it goes. So that's what it sounded like. Do I think it's incidental or inevitable to detect gravitational waves? I guess I don't fully understand the question. I do play the violin, yes. I don't fully understand the question. I think we tried to detect gravitational waves, and LIGO, let's put it this way, we would have been really surprised if LIGO didn't detect anything, because we think things are out there that LIGO could detect, and we think the waves exist. So if we didn't detect anything, we would have been surprised. So in that case, it was inevitable. On the other hand, if you haven't detected something, you're never 100% sure that you will, because it could be that the world doesn't work quite the way you thought. That's how science works. You look for stuff. If you don't see it, you modify your theories. But so far, the theories are doing great. So I predict that we see more, and that if we build LISA, we'll see a whole bunch of stuff. Even advanced LIGO, we'll see a whole bunch of stuff. Good. Excellent. Another violinist. Is it possible to do time travel? No, gravitational waves don't actually help you with that, it turns out. If you want to do time travel, what you really need is a negative energy density, and it's not even clear that means anything. If you can generate a negative energy density somehow, you can build a warp drive, which will allow you to go faster than the speed of light. And once you can do that, in between that and being able to go very fast sublight speeds, you can travel back in time. But that's a whole different ball of wax from, I'm being attacked. That's a whole different ball of wax from gravitational waves. So gravitational waves themselves won't help you with time travel, alas. And as best we understand general relativity, to really do time travel, you have to be able to generate things, negative energy density specifically, that may not even really have a meaning. Oh, for now, we're still stuck with no way of knowing how to do time travel. Sorry. Actually, I'm kind of mad at myself. I'm pretty sure I'm going to invent time travel, and I'm annoyed that I haven't come back in time and given myself the secret. Would you see resonances? Yeah, you would. I mean, you could see resonances. So I guess that's an interesting question, right? If you had a gravitational wave going by an orbiting neutron star, and if the signal was strong enough, it could actually interact with the binary neutron star, right? I think the coupling would be weak enough. It might be tough, but yeah, you might be able to. Yeah, Vic says, or we have to learn about. All right, so what do I expect next new in this field? I think, well, with advanced LIGO, I expect we'll start seeing more binaries. Here's the thing. What I expect is something I didn't fully expect. I didn't expect 30 solar mass black holes. So the next new thing we get will be something I probably don't fully expect. All right. Well, thank you all. I'm going to head out now. So all of you have a good time. Well, you know what I would talk about. There was a indirect detection of what might be 100,000 solar mass black hole in our own galaxy, which would also be, so it's all about the black holes, right? Would be a region of black holes that we don't know about. That's what I was going to talk about here, but instead I talked about this, so I could do that one in another month or so. All right, yes, in Sagittarius, so close-ish to the center of our galaxy. All right, well, I'll see y'all later.